Hello, welcome to week 2 of ERTH413 Geological Data Analysis at the University of Hawaii. I'm Garrett Apuzen-Ito, and this next series of videos will cover section 1.4 of Paul Wessel's notes, and there's also material from chapter 2 of Davis. I recommend that you have a look at that. It's a very nice chapter. I did want to encourage you to make sure you're taking good notes. You should treat this just like any other lecture and take good notes. And the advantage of these videos is, if I start going too fast or you're having trouble copying down equations, you can always stop me and finish your notes and then continue. So I'd like to first read a small section of Davis's chapter that I think nicely summarizes probability. So although many descriptions and definitions of statistics have been written, it perhaps may be best considered as the determination of the probable from the possible. In any circumstance, there are a variety, sometimes an infinity of possible outcomes. All of these have an associated probability that describes their frequency of occurrence. From an analysis of probabilities associated with events, future behavior or past states of the object or event under consideration and under study may be estimated. So as we all know, we make decisions based on what we think might happen. We have some decision of a probable outcome of what we do, or we may decide whether, for example, we may decide whether we want to go for a hike, given that we look at the sky and we don't think there's a good chance of rain. And these choices or assessment of probability comes from a lifetime of experiences and decision making. And here we're going to in this class we're going to more formally define probability, and that will be the topic of these videos. Okay, so the first thing we need to define if we are to talk about probabilities is possibilities. So let's look at the possibilities of some situations. So the first situation I'd like for you to consider is to tell me, say we have 3 dice, a red dice, a blue dice, and a yellow dice, and we roll it. And I'd like to ask you, how many possible outcomes can there be by rolling those 3 dice? So go ahead and hit pause on the video and think about the problem, and when you have your answer, come back and restart it. Okay, so I'm going to give you my answer. So the first, let's say we roll look at the first dice. Let's call that the blue dice. And we know that that has 6 possibilities. Okay. So then we look at the red dice. And we know that it too has 6 possibilities. So between the two, of the 6 possibilities of the blue dice, there are 6 also other possibilities for the red dice. So for those 2 dice, there's a total of 36 possible outcomes. And then finally, when we roll the yellow dice, we have another 6 possibilities. So the total is, of course, 6 times 6 times 6. And that's equal to, what's the answer? 216 possible outcomes of rolling 3 different colored dice. Okay, and so what we just now illustrated is the multiplication of choice rule. And I'll go ahead and write it out. And again, please copy this down in your notes. So if a final result consists of k steps, of which the first can have n1 possible outcomes, the second and 2 possible outcomes, etc. And the kth step can have n k possible outcomes. Then the total number of possible results is the product, write this out here, n1 times n2 times n3 all the way out to nk. And we can write that product as capital Pi for product. It's kind of like capital sigma for sum, but here we're talking about the product, and we're making the product of ni going where I goes from 1 to k. Okay, so that is a general rule of multiplication of choice.
The next topic we're going to cover is permutations, and that's section 1.4.1 of Wessel. So let's consider an example. We're going to roll 4 dice, and they each have a different color. 4 dice, and let's say we have a red, white, yellow, and blue. And let's ask the question, how many ways can we roll 2 6s? So let's consider a 6 is a success, and how many ways to get 2 6s, 2 successes out of rolling 4 dice. So let's look at this. So the first, let's see, so let's say we get our first 6, and there are 4 different ways in which we can achieve that, right? We could get the first 6 on, for example, the red dice. We could get the first 6 on the white dice, and so on. And so we have 4 ways of getting the first 6 between the 4 different colored dice. And now each of those first 6s have to be paired with the second 6, and for each one of those possibilities there are 3 possibilities of getting the second 6. I'll go ahead and write this out, and I encourage you to do the same. Oops, let me do this in order here. Okay, so okay, so we see that the first 6 had 4 possible locations, 4 different, it could appear on any one of the 4 dice, and the second 6 could appear on the 3 other dice. So the answer is there are 12 different ways of arranging or of getting 2 rolls of 6. And so let's write this out. So okay, so let's make this more general. For n dice and 2 successes, the number of ways is n times n minus 2 minus 1. Right? In our case, n was 4, and so we had 4 times 3. And making it still more general yet, let's consider n dice. I shouldn't have wrote dices there. N dice and r successes. We can write n times n minus 1 times n minus 2 all the way down to n minus r minus 1. So that's our initial formula for the number of perturbations of r successes out of n tries. So let's finish up with that equation. So let's make use of let's make use of n factorial. And I forgot to mention, Paul's notes goes through a similar derivation. We're just using a different example. So you can follow this along in Wessel's notes as well. So let's make use of n factorial. And n factorial is equal to the product of I going from 1 to n. Right? Many of you have seen factorial before. 3 factorial, for example, is equal to 1 times 2 times 3. Right. So starting with our previous equation, we had n times n minus 1 times n minus 2 all the way down to n minus, well, I'm going to go ahead and remove that bracket and just type r plus 1. And then I'm going to add some more terms, n minus r times n minus r minus 1 all the way down to 1. Because you can see the way I've written this is equal to n factorial. Okay? But of course, we really only want this part in our solution, so we have to divide n factorial by this part, and that is just, you may recognize it. What is that? How do we write that out in a shorter form? That's n minus r factorial. So let's just divide by n minus r factorial. And this gives us the number of permutations of r successes out of n trials.